Hello again. This is Math 2115 coming to you from the College of DuPage, and the title of this lecture is Counting and Probability 1. Make sure that you are an active learner as you watch this video. Sometimes people say it's as easy as 1, 2, 3. Well, that's the saying, and in certain ways counting is easy, but other aspects of counting aren't so simple. And here's a couple of examples by way of introduction. Have you ever agreed to meet a friend in 3 days and then realized that you and your friend might mean different things? For example, on the European continent, to meet in 8 days means to meet on the same day as today, 1 week from now. On the other hand, in English-speaking countries, to meet in 7 days means to meet 1 week from now. 1 week from now, 7 days hence. And so the difference is that on the continent, all days, including the first and last, are counted. In the English-speaking world, it's a number of 24-hour periods that are counted. For example, if it were Sunday, you would say 1, 2, 3, 4, 5, 6, 7, 8. So you see, Sunday to Sunday would be 8 counts. But in English-speaking countries, you would say, you would count the 24 hours between Sunday and Monday as 1, this one is 2, this one is 3, 4, 5, 6, and 7. Now, the English convention for counting days follows from the almost universal convention for counting hours. If it is 9 a.m. and 2 people anywhere in the world agree to meet in 3 hours, that means we'll get together again at what at least in one time frame would be 12 noon. The difference would be 3. Musical intervals, though, on the other hand, are universally reckoned the way the continentals count the days of the week. An interval of a third consists of 2 tones with a single tone in between. So this is an example of an interval of a third. So you go from C to D to E, but they count all 3. The first and last both count. And an interval of a second consists of 2 adjacent tones. Here you go C and D, and that's an interval of a second. Now, we will be discussing many facts about counting in this course, but I'll plan on using probability as an important context along the way, and so we're going to start there. With a definition. A sample space is the set of all possible outcomes of a random process or experiment. An event is a subset of a sample space. This will become clear later, but that is our definition. If S is a finite sample space in which all outcomes are equally likely, and E is an event in S, then the probability of E, denoted P of E, it's like F of X, P of E, except this time instead of putting numbers in there, you're putting a set. P of E is, the probability of E is equal to the number of outcomes in E divided by the total number of outcomes in S. Now for any set A, the number in A denotes the number of elements in the set, and in our textbook they use the absolute value symbol. I'll make sure that's clear for the context. So if I change this definition to be consistent with our definition here, the probability of E is the number of elements in E divided by the number of elements in S, and in our book they would say that's the number of elements in E, the absolute value of E divided by the absolute value of S, where those absolute values means how many things are in the set. So let's talk about probabilities for a deck of cards. An ordinary deck of cards contains 52 cards divided into 4 suits. The red suits are called diamonds and hearts, and the black suits are called clubs and spades. Each suit consists or contains 13 cards of the following denominations. We have a 2, 3, 4, 5, 6, 7, 8, 9, 10, Jack, a J, Q, a Queen, K, a King, and an Ace. And an Ace has 1 things on it. In some games, an Ace is 1, in some games, an Ace is something else. The cards J, Q, and K are called face cards because they have pictures on them usually. Now mathematicians actually have studied cards a lot, and depending on whose paper you read, 7 shuffles are needed to thoroughly mix up the cards, or in somewhat different definition, you can mix them up in 6, and that almost always works. Now, these are made precise in these math papers, but we'll just talk about mixing the things up. Imagine that the decks in a deck have become, by some method, so thoroughly mixed up that when you spread them out down and pick one at random, you are as likely to get any one card as another. A. What is the sample space of the outcomes? You're picking one card. So the outcomes in the sample space are the 52 cards in the deck. Those are the outcomes that are possible, one of those 52. What is the event that the chosen card is a black face card? Well, black, you either are going to be spades or clubs. In a face card, you're either going to be a jack, a queen, or a king of those 2 suits. So if you look at the set E, it's going to be this set. And then we say, what's the probability that the chosen card is a black face card? Well, the number of events are 52, and the number that are in the event E that we're talking about are 6. So 6 over 52 is approximately 11.5%. Let's look at another sample space and event consideration. So a die is what you call one of a pair of dice. So here is a pair of dice. And a die is a cube with 6 sides, each containing from 1 to 6 dots. And the dots in Britain are called pips. And so we'll talk about 1 through 6 pips. And I think many of you have played with these things in certain games before. Yahtzee or Monopoly or some board game. Now suppose a blue die and a gray die, shown in the pictures here, are rolled together, and the numbers of dots that occur face up on each are recorded. The possible outcomes can be listed as follows, and this is one way to look at it, where in each case the die on the left is blue and the one on the right is gray. And so you see this is all the possibilities, and if you were to count those, you would end up with 36, because we have 6 in this column and we have 1, 2, 3, 4, 5, 6 columns. And so the number of outcomes is 36. Now a more compact notation identifies this 2, 4 with a notation 2, 4, meaning the blue and the gray, 2 and 4. And this is identified with 5, 3, and so forth. So in part A here, in this example, we're saying, let's use the compact notation to write the sample space as a possible outcomes. And so you write all of these things down here, and this is 36 possible events. That is your sample space. And then we say use set notation to write the event that the numbers showing face up have a sum of 6. And then find the probability of that event. Well, we look everywhere where 6 happens, and if we were to look up here, we would say that's 4, 2, 3, 3, 2, 4, and 1, 5. And we also can have that in the I guess that's all the orders of possibilities where they add up there. And so it's 1, 5, 2, 4, 3, 3, 4, 2, and 5, 1. Okay, and so whenever we look at all of those examples, then there are 1, 2, 3, 4, 5. So it is 5 over 36 is the probability. Now let's talk about a somewhat harder problem about the probability. And this is called the Monty Hall problem, because there used to be a show on television called Let's Make a Deal. In fact, it's still on, although Monty Hall doesn't do this anymore. But he was very famous for being the host of this show. Okay, so there are 3 doors on a set of a game show. 1, 2, 3. And we'll call them A, B, and C. So you pick the correct. If you pick the correct door, you get a pick. You win the prize. So you pick door A. The host of the show then opens one of the other doors and reveals there is no prize behind it. You see, there's only a prize behind one door. So keeping the remaining 2 doors, he asks whether you want to switch your choice to the other door or stay with your original choice of door A. Which would you do if you wanted to maximize your chance of winning the prize? Stay with door A or switch? Or will the likelihood of winning be the same either way? And if we were in a class, I'd do a poll and see what you thought and things like that. But now we'll talk through the solution. It is somewhat surprising, I think. At the point just before the host opens one of the closed doors, there is no information about the location of the prize. Thus, there are three equally likely possibilities for what lies between the doors. Case 1, the prize is behind A. And so you see that A is not in here, but case 1 is that B and C are empty. The next case is that the prize is beyond what is in B and not in C, and A again can't have the prize because there's only one prize. This is a case where A wins. This is case 2 where B would win, but A would lose. And case 3, you're putting it in C. Now you see that there's really three cases then. The prize is in A, the prize is in B, the prize is in C. But what Monty Hall is going to do is he's going to show you one of the doors without a prize. And so he could show you B or C here. Here he would have to show you C, and here he would have to show you B. But you see there are three outcomes. Now, which of these then would you win by switching? You would win by switching here, and you would win by switching here. So you see, you would win by switching 2/3 of the time, and you would win by staying only 1/3 of the time. Therefore, you should switch. Now that is a long-term average, but you should switch on average. More generally, if m and n are integers, you know what that is, and m is less than or equal to n, how many integers are there from m through n? Now, to answer this question, you should note that n is equal to m plus n minus n, where that is bigger than or equal to 0. And so this is the way you're going to count them then. And the question was, so we start here and we say this is the 1, 2, 3, and we go all the way up to this one, and that is m minus n plus 1. So the number of elements in the list that I described is n minus m plus 1. Now this is actually an important enough thing to be stated as a theorem, and this confuses many students, I will tell you. And if we were to do a formal proof of this, we would use math induction. The heart of the proof is the observation that we already talked about. If the list m plus 1, up to k has k minus m plus 1 numbers, then the list m plus 1 up to k plus 1 has k plus 1 minus m plus 1 numbers, and that's the key induction step. But here's the theorem. If n and n are integers and m is less than n, then there are n minus m plus 1 integers going from one to the other. That is, you have to count the first or the last, but not both. Okay, let's apply that to an example, counting the elements of a sublist. And these are the kind of questions that I might ask on a test regarding this. How many 3-digit integers, and that means that the integers are from 100 to 999 inclusive, are divisible by 5? And then the other thing I can do is I can ask you, what is the probability that a randomly chosen 3-digit number is divisible by 5? Okay, well, let's just write or think about this. Sometimes you do write things down to think about them. We go from 100 all the way up to, that takes us to 110. We do ... meaning the pattern continues. And we finish this going from 94, 95, 96, 97, 98, and 99. But now we're going to look at, and we're going to see, draw arrows for each integer and its corresponding multiple of 5. So you see 5 times 20 is going to be the 100. 5 times 21 is this. 5 times 22 is that. 5 times, it turns out 199 is this, and there are no more multiples of 5, so that's the last one. So from this sketch, it is clear that there are as many 3-digit integers that are multiples of 5 as there are integers from 20 to 199. See, we did 20, 21, all the way up to 199. So by the theorem we just talked about, how many of those are there? There are 199 minus 20 plus 1, or 180 such numbers. Hence, there are 180 three-digit integers that are divisible by 5. Now, the total number of integers from 100 through 999 is 999 minus 100 plus 1 is 900. And so, to find the probability, we would say it is 180 over 900. It is 1 out of 5. Another application of this is counting the elements of a one-dimensional array. And this is important because analysis of many computer algorithms requires skill at counting the number of elements of a one-dimensional array. So let A1, A2, up to AN be a one-dimensional array like you program in your computer courses, where n is a positive number. So suppose the array is cut in the middle. So we just, there's the whole one, but we just cut it somewhere in a middle value, AM. And so we go all the way from 1 up to AM, and then we go from, this is the first list, and the next one we go from AM plus 1 all the way up to AN. How many elements does each subarray have? So let's talk about that over here. Now, since we said we cut it in the middle, we say array 1 has the same number of elements as the list of integers, 1 through m, because we've talked about that. So by theorem that we just talked about, it has m, or m minus 1 plus 1 elements. We just counted them. Now array 2 starts with m plus 1 and goes up to n. So how many things are there? And by the theorem, again, we find out that it has m minus n, or m minus n plus 1 elements. So you see, we know how many are in the first one and how many are in the second one, and we've calculated those. Now, what is the probability that a randomly chosen element of the array has an even subscript? And it really is going to depend on if n is even or if n is odd. Okay, if it's even, then we're going to be looking at the same kind of scheme. So we're going to be this up to, and this is 2 times n over 2. Remember, n is even, so n over 2 is an integer here. And so that's how many, and we're going to say there were n over 2, because it's the number of multiples of 2, divided by n, it is 1/2. Now, what happens if n is odd? Well, if n is odd, then the greatest even subscript of the array is n minus 1, because this time n is odd, so you have to go back 1. That's the greatest subscript. So there are as many even subscripts between 1 and n as there are from 2 to n minus 1. And the reasoning we've used before can be used again to conclude that we have n minus 1 over 2 array elements with even subscripts. So since the entire array has n elements, the probability that a randomly chosen element has an even subscript is n minus 1 over 2 over n. And if we simplify that, we get n minus 1 over 2n. This is not 1/2. Note that the answers can be combined using the floor notation. We talked about this before, and the answer could be this, which is the floor function of n over 2 over n. Closing. Now, more than ever, time is precious. Each day must count. Do the math. It will make you strong. And now, more than ever, take care of yourself and of each other. May God bless you all.